industry professional, and also a member of our industry advisory board. So we are glad that Dr. Zufan is here to share his knowledge. So now I will pass the floor to Dr. Zufan.
Yeah, okay. Thanks. Yeah. Let me see if I can share my screen. Screen number. Window. This is the audio. Let me know if you can see my screen.
Class, in case you have any questions, you can always raise your hand. Then Dr. Zufan will attend to you.
Yeah, please, please do so. Yeah, I don't want to make this like a very boring Friday afternoon lecture, right? So, okay. First of all, thanks again, Dr. Eugene, for inviting me to share a little bit of the experience that I have working in some places. And then the topic is around process dynamics and dynamic simulations typically. But then for this occasion, let's add on something to that. Yeah. So it's not going to be like a hands-on training because I mean it's online, so it's very difficult to do a hands-on training. So I'll just walk you through some slides. But then I would expect some participation. Yeah, so I would ask questions, and then I think in the chat you can just simply raise your hand or ask questions, and then if I ask questions, and then I hope that you would be answering the questions as well, just to make it more interactive. So okay. I think I changed the title the title a little bit, so it's more like an introduction because there's no way that we can deep dive into this topic in 1 hour or so, not even in 1 year. So just introduction to how we apply process dynamics and control, and then how to see or how to try to relate that to process optimization, right? So it's an introduction to applied process dynamics, control, and optimization basically. I have to say this, so this is me speaking on myself, not representing anybody, and then whatever I say here, it's purely like my own experience, and any these I own the mistakes that I may make or forgotten something. So resources. So typically for students, I would like to put like some of the references for that I typically go back to. So it may be good that so that many of these are on. I mean, all of these are online except for these books, right? You can also find the book online. So I've shared the slides. I'm not really sure if you get this type of link which you can then click, and then you jump to the site immediately. But then you can always what is like process simulation, what is steady states, and dynamic modeling. What difference do they have? And then we see a little bit on the how the process dynamic is used in control very briefly, and also the a concept on process optimization. And then there will be like a demo in HYSYS that I prepared, so that you can try to relate the concept here to a very simple case study. To a very simple case study. And if time permits later on, I will explore or share some of my past projects for your own awareness. Okay, if there's any question, just type in. I don't mind. Okay, now first and foremost, why do we do process simulation? I'm not really sure if you have my slides already, but then could you please think we have 14 people here? Can I have like 14 answers on why do we do process simulation? And you can just type in the chat so that I can see I'm not talking alone. Yeah. Um, so why do we do process simulation? Okay, I'm not going to judge, but come on, guys. This is still like 3 p.m. On Friday, so it's not day is not ended yet. So
Susan, can you see the chat box? Can you see the chat box?
is that what I see? Like 3 replies?
Uh, yeah, can you see the chat box?
I
What
think
the
so.
student have written? You have, can you see it?
Yeah, I see 3, right? I see 3.
Oh,
Okay, very good. Verify manual calculations, mitigate risk, and ensure safety to get 10 credits for my third year. Okay, very good. So, what more? Why do we do process simulation? So, people on the field, right? People on the field, like me, we do process simulation.
can't hear what you say. You are mute.
Can you guys hear me?
Yes, now I can hear.
Okay. I think it's now it's clear, yeah. Okay. Okay, where were we? Yeah, so if you guys like later work in an EPC company or engineering procurement construction or EPCC commissioning on construction commissioning and an EPCC SU including the startup, some of you will design the plant, right? So before to do the proper design of the plants, we'll need to do a proper mass energy balance calculation. And then mass energy balance calculation is basically a process simulation or process modeling. Yeah, you can do process simulation using the well-known process software tools like Askentech or like I don't know, some products from Aviva, or you can also do like model the plants in Excel. Yeah? So I've modeled I think 2-3 plants back in the day with Excel, and then we designed do the mass energy balance calculations in Excel, and then we design the equipment as such. So that's the basic well the most frequent activity why we do process simulation to size the plant to size the process unit operations. And then once we have some form of mass energy balance calculations for the plants, and then typically we will want to use that to find any root cause of the problems, because something may happen in the plant and then we don't know what causing it, and then our first go-to is then to create the mass and energy balance around the problematic unit. So that's the number two over here. And then once we know what the problem really is, and then or we know now the current capacity of the system, we can do then what we call a performance analysis, yeah, or via sensitivity analysis. So for example, if I draw a plant like a black box like this, right? This is a plant, and then you know your feed coming in, right? And then you have your product coming out, and then you have some. So this is the feed, and then this is your product, and then you could also have, well, this is my energy stream, for example, and then the valve somewhere in between, the valve somewhere in between. So you can then say, okay, if I increase this feed to a certain degree, what happens with my product rate, what happens with the purity of my product rate, right? So these things, if you do like some form of, like, I don't know, sensitivity analysis we call it, or trial and error, or to see what is happening if you change one independent variables like this, things that we can control on the plant, and then see what happens. And then if you can then find, okay, what is then the optimum energy amount, optimum whatever flow rate that you need to put into the plant, as much so that you can increase the profitability of the process, and that is what we call process optimization. So one of your colleagues mentioned about process optimization in the chat box. So that's the first three which I've ever done. And then the number four is more like we do a dynamic simulation. So say for example, we have a unit, and then if we want to introduce another set of stream, for example, a new feed stream, say if you have like I don't know, this is my imaginary illustration as we go, yeah. So we have like FA and then FB. This is FA and then this is FB. So if we want to increase this, what happens is there what is then the effect on the whole dynamic in the pun. So typically we will do this dynamic simulation in like safety studies, right? So if we increase, say for example, we want to do like a blowdown studies, we want to increase like sizing the staggering of the process safety valves. So those activities can be done in dynamic simulation as well. So that's for process safety. And then also if we have like a new system coming in, like for example, I have another reactor over here. So we have another reactor there, existing one, and then if I have two reactors over here, how is this two feed going to be separated into reactor 1 and then reactor 2? What's then the control scheme, and then how it is then dynamically going to be operated? So these things, what we can do in using dynamic simulation. And then another one is that if you work in the R&D later on, so we typically have our chemist colleagues with us in the department, and then they can invent all kinds of chemistry routes, yeah. And then our job is that to make sure, so because they can invent like 1, 2, 3, all kinds of chemistry route from feed to products, and then our job is then to evaluate each of these routes, where or which of the routes are the most profitable, or which of the routes are like giving us a better economic profitability, so that we can then so during the R&D, right, during the R&D, and then they give this, and then we can then select some of these routes, right? Either this is, maybe that one, maybe this one. So this phase is what we call like R&D, or feasibility study, or conceptual study, so that we know in the next phase, like in the next phase of basic engineering, for example, basic engineering, you can then say, okay, from this feed to that product, there are only like 1 or 2 routes. Yeah, so this is then what we call the techno-economic analysis study. The concept, I mean, how we do that is basically the same with the mass energy balance calculation. in your plant design. It's just that we need to have more insights on the process and in the economics as well. So which part of the process consumes the energy a lot, or which part of the process is very inefficient, which part of the process that consumes a huge amount of cost. Those things needs to be identified and then need to be tackled in the next phase of the R&D. Yeah, just also saying that showing next direction in the R&D for process development, right? So because we know, so from this stage we know, well, these two are the most profitable, so we get to this. But then these two routes, what are they disadvantages and then advantages that they have, right? So if we see, okay, this is like more safer than this one, and then but this has like huge amount of I don't know, we need to have like a lot more cost compared to this process. So what needs to be done in this route so that we can then reduce the cost as but still maintain the same safety index, for example. And then the last is then to evaluate any modifications and debottlenecking. So I think I have included here already. So if we have like a new reactor or catalytic systems or a new process equipment over here, so or if you want to increase the flow rate by 2, for example, so what are the debottlenecks? What units are becoming the debottleneck for this process? So these are basically what I have done using process simulation as a tool, using process simulation as a tool to solve 1, 2, 3, 4, 5, 6, 7 problems basically. So this is what I think, what I've done on why we have to do process simulation. But then in any case, if you go to the plant, just simply make your own mass and energy balance wherever applicable, and then I can guarantee you that you will see problems, and then you will see then room for improvements, right? So that's what this slide is about. So if you have any question, just let me know. Yeah. Like I said, there's no 10 credit. I don't get any credit here for doing 20 years of process simulation. So what is steady state and then simulation, and what is dynamic simulation? Um, I think you know this already, but nonetheless, just to set the scene. So imagine that we have if we have where's my mouse? So imagine that we have a vessel, right? A vessel like this, and then we have this level, the dotted line, and then we have a flow rate coming in, and then there's a valve there, and then the flow rate going out. And then this vessel has a certain height and then a certain diameter, right? So a cylindrical vessel, for example. So how do we see this system? So if we see this as a steady state, what is a steady state meaning? Is that what does it mean? Is that there is no change whatsoever in the whatever quantities that we are evaluating in time, right? So there's no change of what quantities or whatever quantities that we evaluate in time. So in this case, the quantity is the volume, and the volume of the liquid here in the vessel. So that volume, right? So this volume over time equals to 0. So if this volume is equals to 0, right? So that means you will then have the same level whatever time, and that means the flow rate that's coming in is going to be equal to the flow rate that's going out, right? Because if you have like more flow rate here, you will get a higher level, but then if you have lower flow rate here, you will get a lower level, right? So that as easy as that. But then if you have the same flow rate coming in and then the same flow rate coming out, and then you will get the same level. So that means there's no change in the volume of liquid in the system. So that's what we call like steady state. Yeah. So well, mathematically we write it in this manner, and then it means F in equals to F out. But in dynamic simulation, we know, well, there's nothing in steady state basically. So things happen. So the flow rate coming in is not equal to the flow rate coming out. How much do they not equal? They don't equal by this number. So the change of volume in delta t. So if we have like a higher flow rate coming in, so that means this guy will be higher, right? So that means the change of volume will be positive. That means you will then see a high increase in volume, increase in height. But then if the flow rate coming in is lower, or the flow rate, sorry, if the flow rate coming out is higher, for example, that means this dV/dt will become negative, and then you will have a decrease in volume for time. That means you will then see the height will be lower as well. So this is the basic difference basically between the steady state and dynamic simulation. But then steady state is very easy, right? So you have a F in, F out, and then you can then you don't care what the height is, you don't care what the size of the vessel is. So there's no dimension here, right? So in steady state, the dimension we don't care, dimension, we don't care. But then in dynamic simulations, we care a lot about the dimension. Yeah, we care a lot about the hydraulic, the dimensions of the system, the diameter, and then the maximum height that we can achieve, and then the any elbows, and in the size of the valve, if any, and then the size of the pipe, and then the size of the valve, and so on and so forth. So these things are taken into account. So if we see this simple problem into math, you will see it as a very simple one like this one. So this is our governing equation, right? These are our mass balance equations basically. And then we can then say, okay, volume equals to the area of this vessel, right, multiplied by the height of the liquid, and then we know area is then a function of diameter, right, because a function of diameter is known and fixed. And then the flow rate outlet is a function of the hydrostatic, from here to there, right? If we look at this as the state 0, so that hydrostatic, and then as a function also as the pressure drop around across the valve. So in this case, we have the CV of the valve. So that's the flow rate out equals to the CV of the valve. So CV is basically showing you what resistance is there in the valve basically. And then it's in many cases, I think in most, if not all cases, it's related to the size of the valve. So a valve with a small CV will have a smaller size typically, and then a valve with higher CV will have will be a lot bigger in reality. So that is also a function of this valve characteristic, and then the pressure drop around it, right? Because we can then close and open the valve, and then the pressure drop here also as a function of the height of the liquid, because the higher the liquid, right, the higher, so we'll have a higher energy potential over here, right? So that means we can then push more liquid through the to the outlet, through the valve. So that's basically what this is. And then this delta H is then delta H equals to H, this H minus H0. But then we need to define then what is then H0. If the H0 is 0, and then you get your H is then H. So this H is basically not only this, but also up until there. So this is your H. And then if we put all of this formulation back into the if you put all of this, right, back into that equation, this is what you will get. And then you play around with some algebra, and then you will get this, right? You will get this, and then if you do then a numerical integration, this is what you will get. So the height, the level of liquid at times plus 1 or times plus delta t equals to its previous height plus the change in height. So this change in height, the dH dt, it can be positive, it can be negative, yeah, depending on the flow rate coming in, and then the square root of the height. So that basically is. So C1 is basically all of this 1 over this guy is C1, and then C2 is basically all of this, all of this together. So this is basically C2. So it's very easy derivation for this very simple system. But then in reality, you will have a lot more complicated systems that you can imagine. Right. So so we saw only that dVdt equals to 0, so there's no change in the volumetric quantity. But then practically, we will see that as well. There's no change in pressure, there's no change in concentration, there's no change in temperature. So if there's no change in some of these, that means some of them is in steady state. So basically, say for example, if we have like dPdt, so you get pressure along the temperature along the time, right? So this is time. So the pressure will then stay constant, there's no change. And then if you see this as a concentration as well, or like height or temperature, it's basically the same. So it's all constant number. But in dynamic, you will see it something like this. So it will then move along these blue lines or even more, right? So the pressure or level or concentration or temperature, so they will then change every single time. So that's the basic difference between steady state and then the dynamic modeling. Let me know if you have any question. Yeah. Right. Now, we know now the steady state and dynamic modeling. So how is it used in force dynamic? So I think you can know already. So force dynamic will then see the dynamic of the system. What we need to then do afterwards, once we know the pressure, for example, right? We know the pressure, but we have our set points over here, for example. I don't know. So this is our pressure set point, right? So of course we want to control the pressure of the system around this set point. Yeah. So things like this is very unacceptable, and things like that is very unacceptable. We want to have the systems moving like this, right? So we want to make the system as steady as possible. Yeah, as steady as possible. So that's the use of this process control course that you are taking. Now, I think you know this already. So feedback control. So we have this is our classical feedback control, right? I think you have seen it many times. So we have the set point, and then we have the error calculation. So we have the set point, and then you have measurements from the plant on the variables that you want to control, and then the difference between them is what we call error, right? So this error gets into the controller, and then this control will then do control the output basically. So like how much flow rate or how much temperature, and then at the end of the day, just like opening a valve to increase the flow rate, or opening a valve to increase the fire heater duty, the gas, so that it can burn more, then you get more heat. So that's basically what this guy is. And then if we increase more flow rate or increase more fire duty, what happens to the process, right? So it will then affect the process, and then you get a your new Y, and then at some point there will be like disturbance. There will be like disturbance that we cannot measure. Say for example, some wind blows, right? So wind blows, and then your pipe has no insulation, and then the temperature drops, and then this temperature here will be higher than this temperature here, for example, right? Because there's this wind blowing, or maybe some I don't know, some obstacle somewhere that makes this process flow rate is lower than what it needs to be, what you need it to be. So so this sketch, if you see this sketch, compare this block sketch to this process flow like this. So this is a simple process flow. If you translate whatever symbols here, so for the level control sketch over here, what is Y, what is E, what is P, D, GC, and G? So that's the question. So we have 17 people here. So I hope to see at least 10 answers. So what is Y, what is E, what is P, D, GC, and G in this level system? I don't know what do you call this level system. So because in level system we have no, I mean there's no such thing as Y here, right? Written. I have flow rate in, we have the height of the liquid, in the vessel. We have diameter, we have the F out, we have this valve, we have this level gauge, for example, and then we have this level transmitter, right? So this level indicator, this level transmitter, level indicator controller, for example, I don't know, right? And then we have the control valve over here. So yeah, so again, looking at the chat, see, type in what you think Y is, what do you think E is, P, B, G, C, and G, um, in terms of the process symbols on the right hand side of the slide. Go on. Go on. I'm waiting. Otherwise, we'll just stay here doing nothing, and then because I cannot continue. Yeah. So Y F out, E F out minus F in, P degree of valve turning, DC control, tank level. Okay, more answers. More answers. Come on. So Ryan, it's almost there. Almost there. Not yet 10 credits, yeah. Not yet 10 credits. Almost there, but not yet 10. So help. Please help others. So we have 17 people here. Come on. It's almost there. Come on. Anybody else? Hey, this is not offline, yeah. It's online. I think I need to like call out some name, no? Mm, you guys, you have learned this, right? Oh no, I don't know. Let me know, yeah. Have you learned this process control? If not, then we can skip it. Um, um, hello. Have you learned this process control? So thumbs up or click yes if you say you have seen this before. Otherwise, then also say no that you haven't seen this before, and then I can just explain to you, and then we can skip it.
So do you mind like go through it quickly? I believe we have learned this before, but yeah, I think it would be great if you can quickly run through it.
Yeah, I will. But let me know your answer first, Adrian.
Yeah, we have learned this before.
Okay, no, I mean the answer for
Something.
this. I mean, if we have learned this before, that means we have some sense on what this is, right? So can you type in your answer, and then I will I need another one or two answers, and then I will go through this. You have learned this before, but then nothing sticks, right? So it's typical. That's typical. That is normal. That is normal, yeah. That is normal. Don't worry. Um, so so only Ryan is brave enough to put his answers on the screen. So anybody else? I need to have like one more, and then I will explain. Any guess? If you don't know, then guess it. There's no harm in guessing stuff. Go on. Man, we have only like another half an hour left, right? I have so many slides already. Well, anyway, if there's nothing, if you're like blank, It's Friday afternoon, yeah. I get that. So why is that? Why is this the process variable, right? So I will just if I delete, how do I delete? Okay, I'll use color, different color. So why is our like process variable that we want to look at, right? This is the process variable that we want to monitor, yeah? Process variable that we want to monitor. So what do we want to monitor here in this system? What do we want to monitor? We want to monitor the height, right? We want to monitor the level. We want to monitor the level of liquid in the system. So this y is then the height, because that's what we want to monitor. And then so this y equals to height, and then the error is then the height minus height set points minus height. So you know that already. And then process. Sorry. P is then the controller output. So this P is the controller output, right? So you get the error, which is the difference in height. So you have, like, for example, this is your height set point, right? Height set point. This is your height set point, but then this is your height. So that means you are lacking more liquid in the vessel. So you will need to close this valve, right? You need to close this valve in such a way that you will have more accumulation in the system. That means by closing the valve, you will get, it will then calculate, okay, you will need to reduce the flow rate out. So how do we do that? By closing the valve. So that's basically how we think about that. So the controller output is then the F out. So we need to reduce the flow rate out, and then how do we do that? By closing the valve, right? So CV, the valve OP, opening valve OP, we need to reduce it. So that's basically what this guy is. By closing the valve, you will get lower flow rate out. And then disturbance here, so you can control here, right? But then disturbance is something that you cannot measure, but it is there. So now if you look at this graph, this level sketch, your disturbance is this guy. So you cannot measure this, but this can fluctuate, right? So say, for example, you reduce this already, but then this guy suddenly drops, right? So you don't have any incoming. That means you cannot achieve the set points for the liquid level, right? So this is closed already, but you don't have any incoming, so you will be dead. There's no way that you can fulfill this gap. So this disturbance is basically the flow rate in, right? And then GC is your control. This is basically this whole calculations behind it. So this level level controller basically. So that's the level controller stuff. And then G is your process. So this process is then this whole volume stuff, right? So this whole volume stuff. So that's basically how we translate the this block diagram on the left to the process on the right, or the other way around, from process to the right to the block diagram on the left. Is there any question? Is that clear, Adrian?
Yeah.
Yeah, very good. Yeah. So it's as easy as that. Just it's everything makes sense. Yeah. If it doesn't make sense, that means something is wrong, either with the explanation or the way we think about that. So that's what chemical engineering is. So it's not that complicated. So now let's play around here. Let's play around. So I took it from a textbook somewhere, which I don't remember, but it says like I think this is like a process transmitter. So we don't know what this P is because everything is P. Process transmitter, and then process, I think PI is indicator and controller, and then this is then process variable or valve. I think this is valve. Because here, typically, for example, in this case, we measure pressure, for example, if then P is the pressure. So if the pressure goes up, that means what should we do here? If the pressure goes up, what the valve should do? The valve should open, yeah? The valve should open, right? If the pressure drops, that means the valve should close as well to contain the gas not to escape, so that it can then pressurize the vessel. So that's basically how we read this. And then the same goes with this guy as well. I think it's more or less the same. But then let's look at the coolant here. So we have a process strip, and then we have a coolant here. And then it has, that means if we have a heat exchanger like this, and it wants to be cooled down, so it means this temperature will be higher than that temperature, right? And then this temperature. And then this P is, I assume it should be like a temperature. Right, so this is the process transmitted like a temperature. So this temperature. So if the temperature here increase, right? If temperature here increase, what should we do to the valve here? So we will then have to cool it more, right? So you'll need to have like a more coolant throughout the exchanger. So we will have to open this more, and then if the temperature here drops, that means you'll then have to close this valve. Yeah. So we have like a smaller flow rate. What else do we have here as well? So I guess this is more like if a process vapor and then it's coolant. It's not really clear how the process is working around here, so we will then skip this. So this one. So let's discuss together. I'll spend another minute on here. I'll just skip. Yeah. So you have a look and then see if you can understand this. If not, then you can discuss it and then ask your lecturer or ask me later on if you're stuck. But give yourself a try it and then see if you can understand the diagram. This one as well I will skip. Yeah, this one I will skip as well because okay. I have a demo that I want to show you. But so we have this DME process. You will need to add the control loops yourself. So we have a methanol coming in, and then it goes to this vessel, the holding tank or holding vessel, and then from this vessel we pump it through a series of heat exchanger so that we can have like a 250 degrees C entering the reactor. So it's a fixed bed reactor, and then it is exothermic. So this temperature here is around 360 degrees C typically. And then we have like a bypass once a bypass that bypassing the heat exchanger, right? And then they combine here. It goes there via the heat exchanger, and then the other one goes here, and then they are commingled here, and then it will then be cooled down to 100 degrees C, for example, and then we then drop the pressure via this valve to be around, yeah, somewhere around higher than 10 bar gauge, because 10 bar gauge is then the condensing pressure or pressure at the top over here. And the vapor, this column is what we call the DME column, because this is the reaction. So we have two methanols. It will be dehydrated. That means we take the water out, and then we are left with DME, so dimethyl ether. So if you know like a propellant, so DME is used also propellant and also as an octane booster. So DME being the lightest, it will go to the top, and then the water and then the unreacted methanol go down, and then this DME will be condensed fully, and then we'll have liquid DME sent to storage. And then the water and methanol goes down to the second column, operates at slightly lower pressure, and then we get the methanol at the top, right? And then we recycle back the methanol to the holding tank here, and then the wastewater goes to the wastewater treatment plant. So that's basically how it works. Now tell me, right? If we can spend some time here. So add the control loop. So now you have this PFD or block diagram, I should say. So to make it like more like a process flow diagram, so someone or like some two or some three, tell me where we should have a control loop. So what do we need to control, and then how it is being configured. Anybody? So how do they control the flow rate of the capacity? right? So we need to you need to run this as a certain capacity. So how do you propose to control the capacity of the system? Hello? Yeah, flow controller. Where should we put the flow controller? Right. So you can just say the name of the equipment. Yeah. Just type the name of the equipment. So flow controller in, I don't know, in this. Say for example, it's my mouse. Say flow control in this vessel, for example, right? Or flow controller in here, in between the DO1 and then DO2. So something like that. So make it more specific. Anybody? Come on. This is year 2, right? This is year 2.
Okay, Dr. Zufan, we are referring to the control of what, which process variable?
Like first question is that process variable is the capacity. So the capacity of this DME production. So if you want to control this capacity, so what should be the what should we control? So make sure that we have, like for example, you have 10 kilotons an hour or 10 tons an hour or whatever capacity that you have in mind. So if I want to make that capacity, so what should I do to make sure I can get that number? Or if it's too difficult, okay. If it's too difficult, yeah. Say for example, I want to flow control before VO1, yeah, maybe after pump O2, okay. So let's do this, yeah. Let's use one. So say for example, I have a flow controller before V1. So you say that you have here flow, right? So let's do this exercise. Yeah, this is mine exercise. So this is your first proposal, and then the second proposal is that after pump O2, okay, this guy. So this flow controller here, right? So let's look at option 1. So if we say flow controller here, so if we set the flow rate here, say for example, I don't know, 10, for example, and then it will fill in this level, it will fill in this vessel, right? It will fill in this vessel, right? But then, yeah, if the pump doesn't run, even though you have full flow rate here, it won't happen, right? I mean, yes. So we don't know. I mean, if we can open the valve as full as possible, but then if the downstream here pump doesn't run, and then you will not have. I mean, that nothing is flowing basically. So that's option 1 is we discard that, yeah. But then there is a use though in this methanol, because this is what we call the methanol makeup. Remember that methanol is converted like 80%, so we have only 20% coming back, right? So 20% coming back. So that means we need to add another 80% to make it at 100%, right? So this is what we call like methanol makeup. So this methanol makeup, what it does is then, because the name is makeup, so we just need to make sure we have sufficient level here, because we have ethanol recycle, right? And then we just need to make sure that we have a sufficient level here, so that this pump can pump whatever amounts that we need it to be. So this is like a level control, and then this level control can be connected to the valve directly, or like a cascade to the flow rate, and then from flow rate to the valve. So this valve is just to make sure that we have enough level of methanol in this vessel. So that's the use of this valve. So very good. And then the second option is that this valve here, right? So this valve here, say this exchanger, you don't see any vapor stream coming out, right? So this is like a fully condensed system. So fully condensed system. Um, so that means all of this will be filled. I wrote it. Yeah, I mean I can just put it here. Or can you put it there? Right. So if we see it there. So this will be filled with liquid. All the way here will liquid, and then some part of this will be with liquid. So it is like a submerged bundle in the exchanger because it is fully condensed. So if we then open the valve here, right? So that means we will then draw more through this DME, assuming that the reflux is constant, right? So that means we will then drag this guy to the yeah. I mean, so we will then empty the exchanger in some sense. When we empty the exchanger, we leave some space, right? So we leave some space, and then this space, the pressure will drop. So this pressure 10 bar will drop, right? So this pressure 10 bar will drop. That means you will not get. That means not only DME you will get to the top, but also you will get some of the methanol goes to the top, right? Because the reflux is, well, there's no control on the reflux currently. But then that type of stuff is something that you need to think through before we design the what type of controllers that we need to put into this flow sheet, for example. Yeah. So I think I've spent like a good 10 minutes or so on this. So there will be many control loops around this. So I'll give you to you as an exercise. Just go through the line of thinking as I've demonstrated to you just now. I think you should be okay. Yeah. Any question, just let me know. Now, how do we do, now we did, I mean, assuming that you know then now by then, assuming that you know how to do this control, put the control loops around the flow sheet, and then that later on you will see that some of these control loops they will fight. Yeah, they will fight. There's no time to explain to you why and how they fight. But if you will look at the distillation column operations later on and then think about how we can control it, you will see in some aspects of this writing there. Now we can control it, and then with the base control, so this is what we call like base control. So all of this control loop is what we call base control. So this base control, and there's so many base control around it. So we can also control temperature here, control temperature over there. So these are base control. And then to avoid the control loops of these base controls to fight, we will have like another level of control. Is something that I don't think you will learn in your undergraduate. So there's something we call like a model predictive control or advanced process control. Yeah. So if you go for a further degree, you will learn something about that. Or if you work in the process control company, and then you will learn more about that. So that will then orchestrate. So it will then orchestrate which valve should be open first, and then how much, and so on and so forth. So it won't fight. But then the question is, sorry. Now the question is, so how to tell, right? How to tell how much to what is this temperature, and then for example this reflux over here. Say assume that we have a flow meters here to control the reflux, right? So in the design we can say, okay, I need to have like a certain number of certain amount of reflux, so we can say so. But then the question is how to let know, okay, because this set point as well, that is also set point. Like in this case, where's my see this set point. So how to know what is then the set point, right? So what is then the optimum set point, so that we can make a profitable process out of this, right? So so number one is well, first and foremost, then something that we need to do this mass energy balance calculations. We have the model, and then we have the cost associated to it, right? So we know the cost of methanol. Where's my mouse? So we know the cost of methanol, we know the cost of DME, we know the cost of wastewater, and we know the cost of all of these heat exchangers, these heaters, coolers, fire heaters. We know the cost of electricity and so on and so forth. So once we know the cost of raw materials, the cost of products, and then the cost of all utilities involved, then we can formulate what we call process optimization basically, and then it will then tell you, once we solve it, which I'm going to show you, will tell you how much is then the reflux, how much is then this temperature, for example, and so on and so forth. So that's how the process optimize. And then once we know, once it gives you the set point or the optimum number, it will become the set point, and then the control loops will then try to match that. Yeah, will then try to match. So this, if say for example, if we say like this is 10, so that's the optimal number is 10, so this valve will then open and close to make sure that we will get to 10. The same goes with this temperature, the temperature, and so on and so forth, right? So that's how it is connected to how process optimization is connected to the process dynamic. I'll give you a demo, don't worry. So now just a quick one. So in practice, we have these multiple layers of optimization. So what you have seen so far is that you have seen sensors, right? Which is yeah, I mean, so this temperature element, this is sensors. There's thermocouple here, so it's thermocouple, so that's temp sensors. And then we have actuators. Actuators then what is then moving the valve. So you can see, you know, the valve already, how it looks like, right? So this valve normally goes this valve, and so on and so forth. So this moves in milliseconds, so it will do the calculation in milliseconds, right? That flow controller, level control, and so on and so forth. So it moves in milliseconds. And then on top of that, we have this what we call like a basic control, or the control loop, which is the one that the flow measurements, and the flow indicators, and then flow transmitter, and then flow control loops. All of this is what they call basic basic control level. Yeah, this is not level, this is like basic control basically. And then this is what I said earlier, that this is then the orchestrator for all basic control, because in one APC we have dozens, if not tens, of basic control level. And then on top of this, so this guy will then make sure that we get to the condition that we want. Yeah, we get to the condition we want. We need to get to a certain level, certain pressure, certain temperature that we want. That is then the job of this guy, and this guy will then utilize many of these control loops underneath that. Yeah, so many control loops. It's governed by this one APC, for example. And then in the plant as well, there is not one APC, there are a number of APC, right? And then on top of this, we need to know, okay, they don't need to fight, they have to work together. So what governs it is then what we call like real-time optimization. So this graph, you can find it in this article. Yeah, you can Google this. So so this real-time optimization will then send what we call like a set point, yeah, to all of this, so that, yeah, I know I need to go to 10. I need to go to 10, right? So 10 comes from the optimizer, and then the advanced process control will then say, okay, to go to 10, that means you will then have to increase this, for example. But then to increase that, you will then need to reduce this, because we have only so much, right? And then you will need to, like for example, increase the duty over here, right? So you get more liquid. So that's the job of this orchestrator, the advanced process control, to make sure that it gets that 10 number and the reflux. The 10 numbers coming from this RTO guy, okay, based on the economics. And then above that is what we call like scheduling. So what it means by scheduling is that okay, now we have methanol grade A coming from company A, and then we can only do so much, right? For example, or they can only ship that much. And then the following months or so, we have another shipment coming from I don't know, country B or plant B, also giving methanol, but maybe slightly different grade of methanol, or maybe this is more appropriate for refinery, for example, different types of crude. But then we stick to our DME plant for now. And then you have need to then schedule, okay, when this tank is going to be used, and then when this tank is going to be used. So that is then the part of this scheduling. Yeah, So we will do this scheduling by daily. And then on top of that, we have what we call like a corporate planning. So if you have like a one plant over here, so this is your one plant, plant one, and you have another plant two in Malaysia, right? Malaysia, and you have another plant three in I don't know, in India, and you have another plant four in yeah, you tell me, Netherlands, for example. So and then we have another source C, for example, and then this goes there, and then this can also go here, this goes there, and then this goes here, and then we will then calculate the whole. I'll change the color, the whole profitability of your corporation. Probability of corporation, yeah, not only now the profitability of one DME plant, but the profitability of all 4 DME plants, for example. That is what we call like a corporate planning here, there. Yeah, is that clear? If not clear, then you need to ask me. Yeah. Okay. If just ask me questions, yeah. Just ask me questions. Put it in the chat, and then we can because I will spare some time on the questions and answer. I need to go in 20 minutes. So now we go to the demo. Yeah, I will do the demo. Discard. I will do the demo. Yeah. So suppose now we have a plant, very simple one. Very simple one. So we have yeah, I can open it to you. So we have like this is the theta degree C, 500, whatever, and then this is the composition. So we have the heavies and then the lights and then some heavies, and then we are going to cool it down, right? Sorry, I'm going to heat it up. So this is what is this temperature. So it's 26 degrees, and then the outlet is then 27 degrees. So it's 26 to 27. So it's like 1 degrees increase, right? So we want to heat it up basically. So this is then our duty, our utility, and then it costs us some money. Okay, and then we flash it, and then we'll get some lights here in stream number 6. So we have incoming of I think 1000, right? So 1000 coming in, and then 476.8 coming as the vapor, and then the remaining 523 as the liquid. So the question is that so stream number 1, number 6, and number 7, they all have prices, right? And then this duty also has a price with it. So we just need to make sure that when we run this, what is then the optimum duty in such a way that we have the most profit from this very simple process. So how do we do that? We go to the optimizer. You go to the optimizer. We go to the optimizer, and then we select like a simple one, original, and then we go to the spreadsheet, and then it will give us this spreadsheet, and then you open it, and then you define yourself the process optimization. So you go to spreadsheet, this thing, right? So first we formulate the objective function. So what the objective function is the profit. So profit equals to the feed that we have to pay, right? So we just simply copy paste. So if you can then if you go here, sorry, not here, the stream. So you go here, you just copy or drag and drop to this cell, and you'll get this number over there. And then I just put a dummy price, and then multiply this into that, you get the flow rate times price for the feed. The same goes with the operating cost. So this guy now currently is around 28 kilojoule per hour, which is I think equivalent to 80 kilowatt. And then this is the price for the operating cost, and then we have the top product as here, and then the bottom product there. This is then the flow rate, that's the flow rate, and then each have their own cost. And then we can see here in this dummy process, I put like the bottom product is a more expensive than the top product, right? So the profit is that, of course, the top product plus the bottom product minus the feed minus the operating cost. That's this guy.
Oh, sorry,
Voila.
Zufan,
Yeah.
are you showing the HYSYS
I think I've
interface?
been showing the HYSYS.
Oh, but I just see your slide, simple case. I can't see the HYSYS interface.
Okay, yeah. 1 second. Yeah.
Okay.
I think I shared the window, the entire screen. Screen number 1. Oh, screen number 1. Sorry. Oh, so all this while you don't. Okay. So I don't see any, because I don't see any comments in the chat. So I was like, okay, just. Can you see my ISIS?
Yes, now can see it.
Okay.
Thanks, Zufan.
Let's do this again. So this is the process. So we have stream number 1 here. We have the yeah, we have the flow rate, right? 1000, and we have the compositions. So we have the lights, and then we have the heavies, and then we just simply then the temperature is around, I think it's 26. So we increase the temperature to 27, and then we flash it. We'll get the lights goes to stream number 6, and then the heavies goes to um, stream number 7, right? And then yeah, this is then our independent variable, or the handle, or the things that we can manipulate to make sure that we have some amount to the top and then some amount to the bottom streams. And then we just need to make sure, because all of these, they have some price, right? So our feed materials have a price, products have the price, and then the utilities also have their price. So how do we do this? We can then here click on the optimizer, like I did, and then, because this is very simple one, use the original one and then go to the spreadsheet, and then we get to the spreadsheet that I just showed you. Let's do it here. Right, so I just put in, so profit is feed plus, sorry, profit is then what we sell, the product, plus bottom product minus feed minus operating cost. And then as you can see here, that is then the current results. As you can see here, you can see the top product is, or bottom product is more expensive than the top product, right? So more expensive. No, okay. The question to the class, so we have this heater. We want to increase or decrease this in such a way that we can maximize the profitability. So, you know, this is then the less expensive, or this is more expensive than that one. So what should we expect this duty to do so that we can maximize this profit? So what do we expect this to do? So that's the question. So I'll give you like, I don't know, a few seconds to think. To let me know what this guy should do. Do we need to increase the duty or reduce the duty so that we can increase the profit? Or we want to maximize the profit? So what do you guys think? Come on. Yeah.
So this is a heater, right?
Yeah, this is 26, this is 27, right? So it's a heater. So this guy's giving heat. So do we want to increase the heat or reduce the heat so that we can maximize the profit?
In that case, I think you should decrease it so that less of it will escape to the gas phase.
Yeah, very good. So that's what we would expect. Yeah, that's what we would expect. So now we have the profitability formulated over here, and then you can see the formulas here, and so on and so forth. And then you can go back to the optimizer, like in this case. So currently we go to variables. So we define then the variable. So we define the variable. So the variable is, if I show you, so the variables is basically this duty, which is this number, so C2, right? So if you change this, to, for example, if we change this to if I change this to just change it here because I know the unit. Yeah, I don't know what this unit is. So if I say that 81, right? So that this number will change, and then you can see the profit change as well, right? If this is too quick, so for example, it's 75. So see, the operating, this duty will change, this cost will change, and then the profit will change. So you can then do what we call a sensitivity analysis, play around with this duty, because this is a very simple one. or you can then do these optimizer stuff to make it a bit cool. Well, nonetheless. So if I close this, so these are our variables, and then we put the bound, right? Because we don't want to end up like no vapor or no liquid. So the bound is then 70 lower bound, and then 90 as the high bound. The current situation is at 80, so you can move from 70 to 80, 90. And then the function is our objective function. So in this case, objective function is then the C6, oh sorry, C6, B6, which is this guy. And then we want to maximize it, right? We want to maximize it. We don't have any constraint as of this moment, because all constraints are in equality constraints, like in this case. And then our inequality constraints are the handles that we have. So there's nothing here. And then is there any, oh, this is like a solver parameters, and then we can then now calculate this. Yeah, where's my variable? So if we do, right, so we have this start button over here. Oh, sorry. Right, click start, and then it should think, and then optimum found, right? So you saw, I don't know if you saw, it was 80 and then it goes to 70, like what Ryan suggested. So we want to reduce this, because we know the more expensive product is the bottom product. Then we can monitor the iteration step. So it moves. So the first iteration it was 80, second iteration is also 80, the fourth iteration is 74, and then you can see the objective function increased from 48 to 50, and then ends up at 70, because that is our lower bound, and then we get another 2000 more, right? That's iteration 4. So that there are 4 iterations, we get to the so-called optimum duty to get this to be a profitable process, right? So now, so we have done the optimization. So how do we then translate this to the process itself? So what we need to have, what we need to do is that now we have the new target, right? Which is this guy. So it was 80. Now to maximize the process, we say, well, the new target for this to maximize the process is that to set the duty from 80 to 70. Yeah, to set the duty from 80 to 70 to maximize the profit based on this process optimizations. So now assume, so this is our process model, right? This is the model. So we send this 70 number to the plant, So my plant is also another ISIS. So my plant is, if I minimize this, minimize that, minimize this. My plant is hopefully this one. Yeah, this is my plant. Why is it not going up and down? View. Anyway, I cannot zoom in. So we have a flow control here. I hope you can see this here. And then we have the pressure control here, and then level control there, and then we have this duty. And then I make like yeah, kind of like a translator easily, to make sure that the because it was 80, now we want to make it 70, right? So this is the guy that handles the transformation. So I just make a very simple one, not to disturb. So currently we are at time 0, and then we will then change the duty at 600 seconds. Yeah, 600 seconds. And then the new duty is 70, right? So this is then the optimum duty that we will then impose. And then currently it is 80. Okay, and then I want to reduce this duty by, like, I don't know, from 600 it goes to 79, 700 to 78, and so on and so forth, until 1500 it goes to 70. And then by that time we should then know we get more money. So what do I plot? Is this guy. This is our optimizer spreadsheet B6, which is the profit, right? So the profit is B6, and then we have this duty, right? The duty of this guy, and then we have the thing. Yeah, this is the variable. This is very small because I have only like one screen. Next time we'll have like offline, yeah, to make it more interactive. Let me put it here. Let me put it there. This is the duty. Okay, this is my profits. My profits. Now let's run this integrator. Yeah, I'm just going to run this anyway. So so it's now running. Real time factor is like 5 times faster than the real time, so that we can see the movement. Otherwise, it will be too quick. Because I don't put any accumulations whatsoever in the system. So we can see the profitability is around 4.8, right? The maximum profit was 5.2, right? From our optimizer back in the day here. 5.2, yeah, 5.2. So now it's 4.8, and then this is 474 for the top product, and then I don't see the bottom product. Can I auto scale all axes? Yeah. So I have the 474 as the top product, 5 something as the bottom product, and then 80 is then the current duty. So at 600, as I already code in the control, in the advanced process control, so to say, at 600, which is 10 minutes, and this 5 minutes. Sorry, 600 is, yeah, 10 minutes, right? 10 minutes, 5 minutes. It will drop to 71, and then 72. 79, and then 78, 77, 76, and so on and so forth until the optimum duty, or the lowest duty in this case, 70. And then you will then see accordingly, the flow rate, this bottom flow rate will increase, the top flow rate will decrease, and the profitability will increase as we know it. And then this heat flow it will increase as well. Yes, it will decrease as well. So I have a redundant graph. So I'll close this. This is redundant. Oh, sorry. See, at 10 minutes it gets from 80 to 79, and then you will have a step in the profitability, and then it's very minor. I think the flow rate will change, but it's very minor. And then okay, and then next 100 seconds gets to the second change. So we do like a step change like this. Well, this theoretically doesn't matter, but then I just want to make sure that to you that we on practice we do things slowly but surely, not to disturb the dynamic of the plant too much, right? So our plant is making money. See, from 4.8 to 4.9 now. Now it's 5.0. So you get money by reducing the duty, and then this duty, the new set point, comes from the process optimization that you have done before. So I think yeah, I've demonstrated how this process optimization related to the process control, how the process being controlled now, and how process control is then built upon on top of the dynamic understanding of the system, yeah, or dynamic modeling, so to say. So yeah, 4:20. I need to go in 5 minutes. I think if there's any questions, I will take for 5 minutes, and that's it. We'll just keep it running. Do we have any question? I need to run in 5 minutes. So it's too bad that we don't you don't get to do this exercise, but I think you can do it on your own. Let me know if you can. If not, it's also fine. You still have some time, some years to learn how to do this. Right. Any question? See, he changes the flow rate a little bit, right? So we will have an increase in the bottom, a decrease in the top, but it's very minor. But then the more significant ones is because it's very simple process anyway. So 71, once you get to 70, you'll just simply stop there, and then we get our 5.2 whatever currency number to it. So then once you made this improvement, you tell your boss, I have a new set point for our heater, and then with this we can make more money, and then maybe perhaps you can get your bonus. I don't know. Yeah, so with this I close the presentation. If there's any question in 4 minutes, I will be happy to answer that. Otherwise, then yeah, I'll give the floor back to Dr. Yijing. No question? That's also fine. It's also maybe too much information, I don't know. Well, if there's no question, I think we can close this session, Dr. Yijing.
Yeah. Before that, can we have a photo session? So maybe students, can you just turn on your camera? Okay, as a memory.